stuff. We'll have some today and they'll get a little more complex in the next class. And then we'll have lots of time to do review. So that's our plan. Okay, so today we are going to do some review about the second derivative stuff and inflection points and that. But most of today's class will be starting with our we had one business application example from our previous class, but we'll have a bunch more of them, and we won't finish all of them, but we'll get to that in the next class, first class on Monday. Sorry, Monday or Tuesday for you guys, Tuesday. So these 5 here are kind of what we're doing with our business applications of derivatives, slowly getting a little more complex with each of these. We will get to the first 3 of these today, and the last 2 we will get to with the next class next week. So that's our plan. I've already talked about the final exam with you guys. This evening we will have a workshop. It's not going to be about the business application stuff. It's just going to be about finding minimums and maximums and inflection points, and then looking at an original plus a derivative and like what this thing curves that way, and that's why that one's negative or positive or whatever. So that kind of stuff, not in the business applications. That will be next week's workshop. All right. So let's exam stuff, talk about that view. So let's see if we remember from last time. How can we find an inflection point? That's how we find the turning points and then see if they are maximums or minimums. Find the first derivative, set it to 0, solve for x, and then check what type it is using the second derivative. Inflection points are a bit different. Okay, so we do the same idea, but with the second derivative. Find the second derivative, set that to 0, solve for x or q in this case. Okay, go ahead. We had this example in the previous class, but we didn't do inflection points. We just did turning points. Just the inflection point or points. You tell me how many there are. Find them. You can work on it. All right, how many inflection points do you think there are? Some say 1, some say 2. Okay, tell me the Q values. 2 equals 2. So there's 1 inflection point at that spot. Okay, so before we even do the derivative stuff, let's just see what we can know about this function. So cubic, so our shape here, it's positive. So it could be, and we did actually see the exact version last time, but we have kind of these things here, right? It's one of these 3 things. So what is the highest number of turning points that's possible? So turning points, most that's possible is 2. It could be 0 or 0 here. So based on that, what's the most number of inflection points? 1 here in the middle. So your exponent minus 1 is the largest number of possible turning points. Exponent minus 2 is the largest possible number of inflection points. So just based on us seeing this as a cubed here, at most 1 inflection point. Can't be more than 1. All right, let's actually find it here. So our first derivative, TC prime is Q squared minus 4Q plus 3. And our second derivative, TC double prime, QQ minus 4. We set that thing equal to 0. So when our second derivative is exactly 0, 0 equals 2Q minus 4. Very easy to solve. 2. So finding these inflection points often isn't actually that bad because our function here, Q cubed, and then by the time we do 2 derivatives, there's no more exponent here. It's just Q. It's just or exponent of 1. So pretty easy to solve. So Q equals 2. We have an inflection point here. And we have these 2 other, if we remember from last time, these turning points at Q equals 3 and Q equals 1. We kind of notice the sort of symmetry, same distance between each of those points there. Doesn't always happen, but will often happen. All right. So that's where the inflection point is. Can you describe to me what an inflection point is? What happens there? Okay, so before this point here, we have this curving down pattern. The slopes are sometimes positive and sometimes negative, but the whole time they are getting closer to negative infinity. They're getting more negative. And then on the other side, sometimes negative, sometimes positive, but the whole time they're getting closer to positive infinity. So curving down, then curving up, sort of slowing down, then speeding up like that. All right, so that's the concept of an inflection point like this. All right, so let's do that again here. Same example I showed you last time, but just show me that you remember. How many curving up and down intervals and how many inflection points can you see here? All right, 2 up, 2 down, total 4. And 4, and then 3 inflection points. Tell me approximately where the inflection points are. Okay, so somewhere between these 2, looks like it's maybe about there. And another one. It's a pretty big range. Okay, so when our x is equal to 0, so or pretty close to there. Okay, that's another one. And yeah, so somewhere a little more than 1, maybe about there. So we draw our lines, split up the function like this, and then we can see we have this curving down, then up, then down, then up like this. So the basic shape, again, a curving down kind of looks like a negative x squared graph, and a curving up looks like a positive x squared graph. So we can just see that shape repeating, just flipped upside down like this. All right, so 4 intervals total of curving up or down, and 3 total inflection points. Also 4, so our exponent here was 5 minus 1, total 4 possible curving up or down intervals. 5 minus 2, maximum 3 inflection points. Lots of connections like that. Right. So a little more review here. Okay, lots more of this. We have these 3 basic types that could happen. We could have nearby turning points, and then our inflection point is happening right between them. We could have, like here, no nearby turning point. And there could be a turning point somewhere else on the function, but there would have to be another inflection point before that happens. So nearby turning points, no nearby turning points, or the special case where it kind of looks like a turning point, but then we realize it just goes exactly flat, but then continues in the same direction. But with each of these, we do have this curving down and then curving up. And curving down, not as much, it never actually goes to negative slopes, but still is part of that curving pattern. And so each of these, the curving type is changing here. And of course, each of these could be reversed so that the right side is going down, left side is going up. All right, so 3 basic types we should be able to identify. And I showed you this last time as well. In total, these 4 different types here. So minimum points, maximum points, inflection points, and then this kind of special case here, again, where it just goes perfectly flat and then continues. And then how we find each of those things. We've been talking about all these already. This is just sort of a summary slide of it. I won't spend too much time here. And notation. So 1, 2, 3, 4 ways to write first derivatives, and then matching 1, 2, 3, 4 ways to write second derivatives. These 2 here are especially kind of strange or confusing looking, but we just have to remember them as a block. That thing means second derivative. So you should be able to understand any of these notations here. All right. Any questions up to that point from what we did? All right, last bit of review was this. And I told you to stare at these graphs until they make sense. So our relationship between the original function and the first derivative, we talked about for a while. And we see we have these turning points of the minimum and maximum perfectly match up where the first derivative is 0. The y values are 0 there. And we talked about this relationship between the original and the second derivative, and the inflection point on the original perfectly matches where we have this 0 for the second derivative. And then it gets, we just kind of throw all that together. And it gets a little more complicated, but still the same information. So if it's still confusing for you, keep staring at this and then keep reading these parts on the side until it does make sense. Any questions about this graph and these connections here? No. All right, so let's we'll do a little bit more. We'll just kind of repeat what we solved here for this question, and then we'll get to the new stuff here. So we had this situation, and we want to find a maximum total revenue, and we didn't have a total revenue function. We only had this demand function, this connection here between price and P and Q, price and quantity sold. So total revenue, what is our basic formula for this? All right, P times Q. And how did we use this to make it? Okay, so we just substitute this whole thing in for P. So we had 50 minus 2q times q, so 50q minus 2q squared. And we also talked about this thing here, MR. What does this represent? Okay, what is marginal revenue? One more time.
Revenue for
Okay, I want a little more detail, a little more clarity.
revenue for each extra unit sold.
Okay, can we heard that? Can you try again, also? That's the math version of it. I just want the concept. You're close. You want to try? Okay, so if Q goes up by 1, how much does total revenue change by? So if we go from Q being 100 to Q being 101, how much does total revenue increase or possibly decrease by? What's the change in it? So if Q goes up by 1, what's the change in our total revenue? That's marginal. So marginal is what's the change from doing one more thing? If this goes up or down by 1, what's the change in the other thing? And we talked about how that is slope. Revenue. That concept perfectly matches the concept of slope. So from that, we discovered that marginal revenue is the derivative of total revenue. We just find the derivative, and then that will tell us the marginal revenue. That gives us the slope at all these points. So for this case here, we found this derivative. It was 50 minus 4q, and we set that equal to 0. Oh, yeah, sorry. That's there. And 0 was 50 minus 4q, so q is equal to 12.5. So this is the same example we did last time. We're going to use these numbers again, which is why I'm showing you this again. Here we had this graph. So we saw that we have our original function. So it's a negative 2q squared as the leading term. So we get this curving down pattern like this. The first derivative, it's linear. So straight line, negative slope. And we have this 0 point right here, intersection with our x-axis turns out to be 12.5. And then we took this. How did we go from this, though, to get the actual maximum total revenue? All right, so this goes back into our total revenue equation. So when Q is equal to 12.5, total revenue was 50 times 12.5 minus 2, 12.5 squared, and that turned out to be 312.5. And that looks about right given our graph. That maximum point seems like it lines up right about there. So we just use our derivative and we find first where the maximum is happening at Q equals 12.5, and then one more step to get the actual sort of Y value of that point, the actual maximum total revenue. All right, let's do another one of these. But just before we go to that, here's our demand function in terms of P. So Q something turns out equals to P, but here's a different one where we have P something equals Q. Okay, so if we can flip this, so Q equals 120 minus 3P, and we want to just rearrange to solve for P. 3P equals 120 minus Q, so P equals 40 minus Q over 3. Okay, so did we need to do this? Did we need to rearrange it in terms of P? No. Okay. So let's think about what we could do here. So total revenue P times Q, and we could do it the way we had before using this thing. So 40 minus Q over 3 Q, so 40Q minus Q squared over 3. Or we could have had this where we substitute in this Q value. So Q 120 minus 3P and 120P minus 3P squared. So we could express our total revenue in terms of Q, or we could do it in terms of P. Mathematically, they're both fine. Which one do you think might be more useful?
First one.
They are connected. So which one? Something about quantity. So we want it in terms of Q. This is the more useful one. I did, but we could express a marginal revenue in terms of P as well. Like mathematically, that's still possible. We do prefer Q, but why do we prefer Q? Okay. When we talk about total costs, what does a total cost equation look like? Okay, so variable cost plus fixed costs. Fixed costs are just a number, just some constant, I don't know, 1,000 or something. What does a variable cost look like? Okay, so cost per item, I don't know, let's say 50 times Q. Okay, so if we're going to make a profit equation, it's much more useful if we have the same variable in each. Otherwise, we'd have a profit equation that's built on both P and Q, and it turns into this three-dimensional graph, much harder to work with, much harder to look at and think about. It's way more convenient if we can express cost and revenue in terms of the same thing. Then we can just combine these two and make a nice simple profit equation, and we can do lots of stuff with it. So mathematically, both are possible, but we prefer the situation where we express everything in terms of Q, because that lets us connect the two ideas. That might feel a little bit weird because you as a consumer, your brain works this way. You look at the price and then you decide, okay, here's the price. I'm going to buy this many of them. The price is determining what quantity you will buy. It's not where you first decide for something that you don't need, you just kind of want a leisure good. You don't say, I want exactly this many of them, and then, well, therefore I'm going to pay this price to get them. You determine how many you're going to buy based on the price. If it's a high price, you're not going to buy a lot. If it's a low price, you'll buy more of them. So this is the way that consumers work, where P is determining Q, but we just do our little mathematical rearranging to do this so that we have our total revenue in terms of Q. So sometimes we have to change around our demand function a bit. But yeah. Isn't that what we did? Solve which one in terms of P? The demand function? That's what we did. It's solved in terms of P. Oh, that's not. It is, yeah, so P equals whatever. This is solved in terms of, or sorry, yeah, okay. I guess yeah, my terms are getting a little confused here, but we've solved it with P being sort of our Y value here. This is our focus. And then Q is the independent variable, and then same independent variable here. Okay, you can ask me after class if you want to go. All right. Okay, so a little bit of rearranging, but the rest of this process is going to be the same. We will just find our marginal revenue, which again is the derivative of total revenue, which is minus 2, let's just write it this way. We'll write it this way, 2 over 3 Q. All right, and we set that equal to 0. And say 0 is equal to 40 minus 2 over 3 Q and 60. So our Q is 60 here. All right. So that's where our maximum revenue is happening. But we need, or we want the actual value here. So again, we're just going to take this Q value, substitute that into our total revenue equation here. Total revenue is 40 times 60 minus 60 squared over 3. And we get a number. We could, yeah. We have a common factor of 60. However we want to solve it. The result here is 2,400 minus 1,200, so 1,200. So there is the actual maximum total revenue. And we found that based on this Q value here of 60. And here's the graph of this scenario. We can see we have that 0 here for the first derivative happening at 60. And we just line that up here. And 1,200. And that's the same number we got here. So there we go. Okay, so a nice simple kind of version of this problem. Just it's a quadratic function. We just use our derivatives, find the maximum, then just one little extra step to get or use our derivatives to find the location of the maximum, and then one more step to find the actual maximum. Okay. Any questions? What's this example? No? All right. Okay, so we have another one, and it's going to get a little more complicated. We have this demand function, and we have this total cost function, and we want equations for total revenue and for profits. So see if we can remember how to make those. Take a moment right now. Mm-hmm. You tell me. All right, so total revenue, it's actually so it's actually the same one that we had before. So 50q minus 2q squared. Yeah, we could define total profit we could calculate total revenue in terms of profit minus cost, or profit plus cost, but we can't. Profit is the result. We're going to start with revenue and cost and use that to figure out profit. So our total cost is over there, 160 plus 2q. Yep. And so profits then is, okay, tell me the basic definition. Okay, revenue minus cost. So it's just these two things. 50q minus 2q squared minus 160 plus 2q. Okay, and tell me the results with in order of the exponents. So largest exponent first. Okay, so we'll simplify. Plus 48q. That's 160. Careful with the signs here. This is plus 2, but there's a negative outside the bracket here, so that becomes minus 2q. So 48, not 52. Okay, so there's our profits equation, and we are being asked to find two different things. First one is our break-even points, and then second one is maximum profit. Okay, how do we find a break-even point? Okay, where profit is equal to 0. Not the derivatives. Derivatives are for other things, but break-even points, we don't need to touch the derivatives yet to figure that out. So break even, we set our profit equation equal to 0. So that's just 0 is equal to this thing, negative 2q squared plus 48q minus 160. And we're just solving for q with this quadratic here. What's the first step you would do? 2, a little more. Okay, so the negative 2. We'll take out our negative 2 so that our coefficient on our leading term here is just a 1. So we'll be left with q squared. What's the rest? Minus 24q plus plus 80. Okay. All right, so that's a little simpler. And how can we try to solve this thing? Yeah, factor? How? Okay, so we can use our, or lots of methods, but our sum product method, we can try that. Do we see two numbers that add to negative 24, but multiply to positive 80? Negative 4 and negative 20, add them together, negative 24, multiply them, positive 80. Okay, that's going to work. So 0 is negative 2, q minus 4, and q minus 20. All right, I'll kind of skip some of the little details here. So this means that q is equal to 4 or q is equal to 20. So 2 break-even points for this function here, not 1. That should make sense. Our profit equation, we have a negative quadratic. We have this kind of shape. So the break-even points are happening where the profit is 0. So this shape is going to hit the x-axis 2 times. It has 2 zeros, so 2 break-even points. That makes sense given the equation that we have here. All right, that's most of this, but we were also asked to find the maximum profits. How can we find that? Largest Q, you mean this one, 20? This is a break-even point. Profit is exactly 0. This one also is a break-even point, so the profit is also 0. How do we find a maximum point? Derivative. This is the original function. This break-even here is the original. We need to find and then use our derivative. So max profit is going to come where, well, first of all, we need our derivative. So profit prime here. What will that be? Negative 4q plus 48. That equal to 0. 0 is equal to negative 4q plus 48, and therefore q is equal to 12. Okay, so that's where the maximum profit is happening. One more step here. How can we find the actual maximum profit? Into which equation? Okay, so we will take this Q value, the location of our maximum profit, and then way back here into our actual profit equation, and that will give us our maximum point. So where Q equals 12, underneath, profit is equal to negative 2 times 12 squared plus 48 times 12 minus 160. Calculator. I saw you typing it in. So 12 squared, what's that number? Okay, 144. So times negative 2. All right, so negative 288. And this number 48 times 12. You knew that? Yeah. Okay. So I would do 50 times 12 is 600, and then we're just subtracting 2 times 12 because 50 minus 2 is 48. That's 24. So 600 minus 24, 576 minus 160. This one is exactly half of this one. So 288 minus 160. And we can see 128 there. Okay, so finally, we got our answer and our maximum profit here. Again, we can notice this is a nice, simple, symmetric function. So we had our break-even points, our zeros of 4 and 20. And then our profit here was 12, exactly halfway between these two things. Won't always happen, but can often happen. Okay, so from just a very simple thing, just a small demand function and a small total cost function, there's actually a whole lot of stuff we can do here and figure out total revenue and profit and break even. And we could also find a maximum total revenue, or we did actually in the earlier examples, maximum profit, all kinds of stuff we can do from just a pretty simple starting point here. Questions about this here? All right. So these questions can get a little bit confusing. Just how do we find each of the things? Okay, break-even points are zeros of the original function. Maximums are zeros of the derivative. So just which things come from which results. If you can remember that, then just find each of those parts. So I'm going to show you the graph. I need to erase some stuff to get to have space for it. Let's get rid of here. Break-even points and maximum profits. Very awkward. Okay, so now we can actually see our graph. And remember, this is the same example with this total revenue maximization thing from last time. And that's not quite right, but our maximum point we discovered was when Q is equal to 12.5. But now we've discovered that our maximum profit is happening at a different point, and it's 12. So similar, but not the exact same point here. And that's because if we look at our total cost equation here, it's not flat, it's increasing like this. So on the right side of this total revenue function, costs are a little bit higher. On the left side, costs are a little bit lower, so profits a little bit higher. So that kind of makes sense with what we've been looking at here. Lots of things we can see with the connections between these functions here. What else? So the height here at this maximum profit, this is also equal to the height between the total revenue and the cost at that point, which makes sense because profit is revenue minus cost. And we can see this 0 here, that's this point of intersection, this 0, this point of intersection, etc. So all these vertical heights here match the vertical heights of the profit equation. Okay, so big takeaway is we can't assume that maximum profit and maximum total revenue happen at the same place. It could be that your maximum total revenue happens at one place, but also the costs there are really high, so it's actually terrible profit, and you get much higher profit somewhere else where your revenue is a bit lower, but your costs are way lower, so a larger difference between the two. We can't assume that they're going to be the same. We have to calculate, find each of them separately. Okay, this makes sense so far. All right, and I think this will end up being our last example for today. So this will be a more complex version of total cost. And then in our next class, we'll start combining this with our more complex versions of total revenue. Okay, what do these things represent here? What is TVC and TFC?
Total variable cost and total fixed cost.
All right, so total variable costs and total fixed costs. So if I want to find my total costs, then what can we do?
We need to add both of them.
Yeah, just add them. So your total costs are just the sum of all of your separate costs. So 1 over 2 cubed minus 15 q squared plus 1 5q plus 500. Because there are lots of things that go into variable costs and lots of kinds of fixed costs. So your fixed costs are, I don't know, building the building and paying someone to like design the original product and paying the safety inspectors to come and check your building and make sure it's ready and I don't know, whatever. There are many kinds of fixed costs. So we are just sort of like ignoring the details here, but your fixed cost, you actually have like, here's your list of like 50 different things that are all different fixed costs. We're just saying we add all those together and we get this. Variable cost as well, you have multiple kinds of variable costs, the labor and the parts and the shipping and the manufacturing process and lots of things. We're just kind of saying we take all that together, here's the result of those two. Okay, so total cost is this thing. We want minimum marginal cost. Minimum marginal cost. So for this function here, do we have a minimum cost? A minimum total cost. Okay, so all right, let's try that. Let's see if we can actually find a minimum here. Not in class. So our derivative, let's do this in green here. Derivatives will find the all turning points, minimums or maximums. It depends on what your function is. So if we have this function and we find the turning points, it will turn out to be a maximum. If we have this kind of function and we find a turning point, it will turn out to be a minimum. The second derivative test confirms for us what type we have, but first derivative will find all the turning points. Okay, but we have a cubic here. So there's a few different possibilities. There could be turning points or there could not be turning points. So let's just kind of think about that first. So derivative of our total cost equation here is what? 3 over 2 q squared. Where is the 225 coming? Okay. 15 squared, yeah. So 30q plus 175. Remember our constant rule, this thing is just going to disappear from our derivative. Okay. So same question, do we have a minimum point? Okay, that's how we would find it, but we don't automatically know. Again, this is a positive cubic, so we could have this shape, or we could have this shape, or we could have this shape. So there might not be a minimum point. Well, the original here, however we can figure it out, so the derivative can help us find out if we have a minimum. But for these graphs, these shapes here, these are the cubics from the original. All right, so what we can use, if we think maybe there's not, we don't really see an easy kind of sum product method for factoring. How can we do just a quick test and see if we have some? We can use our quadratic formula. So negative e plus minus square root e squared minus 4ac over 2a. And then the square root part of that, e squared minus 4ac. This, the discriminants part, if we put in our ABC there and it's positive, then okay, we have roots. If it turns out to be negative, then we don't have any, or not any real roots. And that would mean no turning points for the function. So let's try that out here. B squared square root of b squared, so negative 30 squared minus 4 times our a, 3 over 2, and our c, 175. And that will equal square root of 900 on the left. And what are we going to have on the right here? Now 1020, you're pretty close. So I would think 4 times 175 is 2 times 350, which is 700. And then 700 times 1.5. So that's just plus another 350. 1050. So this square root thing is going to turn out to be negative. So no real roots. So no turning points, no minimum. All right. So this function is just constantly increasing. And that makes sense. If we had a total cost function and somehow, like, to make a new thing in your factory, you have to buy the parts, you have to pay for the labor. But when we make one extra thing, our total cost decreases. Like if we make a new thing, people pay us money to make it. That's like we sell it afterward, but they don't come give us money just to make it in the factory. So that wouldn't really make sense. So a total cost curve like this usually will have no turning points. It does have an inflection point. So, and that's what we're finding with our minimum marginal cost. That's what we care about here. Okay, so discriminants, just a little side thing, we can realize no turning points here. So let's look at our second derivative. So we can find the inflection point. What's 3q minus 30? How do we find inflection points? Okay, we set this equal to 0. So that's 0. And then we say 0 is equal to 3q minus 30. And this is really easy now. Q is 10. Okay, so that's where the minimum marginal cost is happening. And I'll show the graph in a little bit and kind of, again, just sort of explain some of the theory background of that. That's where it's happening. And if we want to figure out the actual minimum marginal cost, what can we do? Minimum marginal cost.
Substitute to the first prime formula.
Okay, to the I forgot to write that here. Sorry, this is. I think we talked about this previously, sort of indirectly, but our marginal cost, it's the exact same thing as marginal revenue, but for cost. So marginal cost is equal to the derivative of total cost. I should have mentioned that before. So if we want to find the actual minimum marginal cost, we'll just take, well, this is where it happens when Q equals 10. And we're just going to substitute that value into the marginal cost equation, not the original one. We don't want minimum total cost because there is no minimum total cost, but we do have a minimum marginal cost. So here, so when Q is equal to 10, our marginal cost is 3/2 times 10 squared minus 30 times 10 plus 175. And I worked out 25 here. So 150 minus 300 plus 150 plus 25, so just 25. So here's the location of our minimum marginal cost, and then here's the actual minimum marginal cost. And here's our, oh, I thought I had these slides set up a little differently. 1 second. No, I do. Okay. I was just swiping in the wrong direction again. There we go. Okay, so this is the graph of the function here. And we can see no turning points. The slope does go kind of shallow, pretty low, but it's not 0. So again, no turning points. But it does go to a lowest possible slope. And it seems like that's happening here when Q is equal to 10. Do you remember our discussion of why this happens? Why would a total costs function sort of curve down for a bit and then later curve up? I did talk about it. This was a few weeks ago. Why does this total cost equation kind of curve down here and then curve up later?
Economies of scale and diseconomies of scale.
There we go. So just efficiency, economies of scale, which let me write that down again. All right. Economies of scale is the fancy economics way of saying efficiency because you do a lot of things. And then diseconomies of scale on the other side is inefficiency because too many things. So on the left side, it becomes more efficient. If we make one thing in our factory, there's lots of waste. But if we make 10 things, okay, we can have like specialists doing the work or whatever. It becomes more efficient up to Q equals 10. And we haven't talked about the product, so maybe Q equals 10 actually means like 10,000 or something. So up to this point, we get more efficient, but if we go over that point, it becomes inefficient because we're just making too many things and it's too hectic, it's too hard to control, extra costs or whatever. So we have this point here where our marginal cost, the cost of making one more thing. So the cost of making unit number 10 is exactly $25 or pounds or euros or whatever. So the marginal cost at that point is exactly 25. That's the lowest possible marginal cost, which also means it's our lowest average per item cost, which is also a nice total thing, like a overall lowest average cost. So that's what's happening at this inflection point. A little more complex than just saying maximum, minimum, because it's now marginal, but it is a minimum marginal cost. So that's why we care about those points. Right? Questions? How much of this have you talked about in your microeconomics class? Not yet. The economies of scale, diseconomies of scale, haven't talked about. Okay. So that'll come up. If not then in macroeconomics. But this, yeah. So just basically efficiency up to a point, and then inefficiency, it just gets inefficient, and then you kind of don't want to go past that point. All right, so minimum marginal cost, we do our second derivative to find the inflection points, and then we substitute that back into marginal cost equation, not the total cost. So which derivative is giving us the information that we want, and then which thing do we substitute that number back into? That's going to be a confusing thing here, so please try to keep that straight. Which function gives us which results? How do we use them? All right, we have more of these, which we'll get to in other classes. All right, so hopefully by now we're pretty good at finding just maximums and minimums. First derivative, set that equal to 0. And we can also find inflection points. Just find the second derivative, set that equal to 0. We'll have practice with that stuff in the workshop this evening. And we've started doing this stuff. We can find a marginal revenue and a maximum total revenue based on that. We can find break-even points. If we have multiple break-even points for a function, we can find both of them and maximum profits. And we can also make equations for marginal cost and minimum marginal costs. And these two relationships, very important to remember and understand. Marginal revenue is just the derivative of total revenue. Marginal cost is derivative of total cost. That was it. If the second derivative stuff is still confusing for you, again, stare at this thing until it makes sense. All right, so more business scenarios, and then 3 more to go through, and then we'll have a bit of extra time in our next class. I might add one extra derivative rule that tends to be useful. We'll see how the time goes. And then our second class next week, we'll have 3 classes of review. Second class next week will just be a review of kind of the formulas and the processes, not actually doing practice questions. It'll just be, here's our methodology for all these different types of questions. And then in week 15, we'll have one day that's all pre-midterm material, and then another day that's all, yes, pre-midterm material, also on the exam. And then the other day will all be post-midterm material. So lots of review coming up. Hopefully that will help us all do very well on the final exam. Any questions before we finish? Yeah. The pre-midterm material is 25% of that, and the post-midterm material is 75%, and that gives the balance that each end up being the same amount of your total grade. Other questions? All right, we are finished, everyone. I will see you maybe this evening for the workshop, and then on Tuesday for our next class.